Welcome back to the concrete design series. In this presentation, we will cover the behavior of reinforced concrete beams subjected to flexural loadings, in particular the singly reinforced beams. Hopefully by the end of this video, you will understand the behavior of concrete beams in respect to the moment curvature relationship. I think we'll focus on today the moment curvature relationship. We will look at each stage of the concrete beam under loading that is significant to our design, and which in other words, what happens to the concrete beam elements as load increases in respect to the beam's flexural behavior and the corresponding curvature. So let's start with a simply supported beam which is reinforced, and it has a single layer of reinforcement, and there are two concentrated forces P star positioned symmetrically as shown here. We have a distance x from the ends and x1 between the point loads. So the term singly reinforced just means that we have steel at the location where tension will occur, this dashed area here, and that represents the reinforcements. So in cases where we don't have any end moments, tension is primarily will be at the bottom of that beam. So this beam will be sagging under the load, which will give you a deflection that looks like a happy face. So there would be a compression at the top and tension at the bottom, like this shown image here in the 3D image that we have done here. So do you know why I chose this beam model with this particular loading configuration? I think the answer is right here. Well, simply because this is a standard setup that is usually presented in the labs for testing to assess the behavior of beams under pure bending. Like we've shown a picture here of the setup in a lab of this beam here. The reactions at the support would also be P star. So between the two loads, we will have a constant moment, as you can see here in the bending moment diagram. We will have a constant moment of a value P star times x. Okay, that's the lever arm x. As we recall from the bending moment, the area, to figure out the bending moment, the area of the shear force. We need to work out the area of the shear force. So if we have a shear force P star and the x here is, and the length here is x, therefore the area is Px, which is the maximum bending moment here. If we neglect the dead weight of the beam, okay, because dead weight will give you that uniform distributed load. Let's assume we neglect the dead weight. Now this region here between the two concentrated loads will be under pure bending, zero shear force and zero axial loads. Now before we get into the moment curvature relationship, we need to be able to draw all the relevant components of the beam cross-sectional and the notations and the notations that is required. Now this is extremely important. This is an important step before we start any beam designs. So if we take a section AA here throughout the beam, we will get an image that kind of looks like this. Now this section is obviously a different scale to the beam. Okay, I've drawn it like that so it can be clear. Now I'm guessing most of you by now would understand how this works and how all the notations and the basic requirements that you need to show in this section, but we will go through the basics again. So here we have a beam depth D, beam width B, and that's a constant width through. The steel bars here, we would note it as AST, and that's the area of steel, and that is generally in millimeter squares. The beam effective depth DST, which is the distance from the center of the reinforcement to the top extreme compressive face of the beam. In this case, the beam is sagging, right? So it will end up being from the center of the reinforcement to the top compression, right at the top, the compressive face of the beam. And C is for the cover depth, which is from the bottom of the beam. In this case, anyway, because the reinforcement is at the bottom, so it will be from the bottom of the beam to the underside of the reinforcements. So, for example, if we say we have 400 wide by 600 deep beam with 4 and 16 bars at the bottom and 30 millimeter cover, here we will draw the section something like this. So how do we calculate AST and DST? Okay, let's have a look. We have the cover, the bottom cover is 30 millimeters, and we will assume also the side cover is 30 millimeters as well, okay? DST, the effective depth is simply 600 minus 30, minus the cover 30, minus 16 divided by 2, which is half the bar diameter. And that will be 562 millimeters. And the reinforcement area is 4, we've got 4 bars multiplied by pi d squared over 4, and d in this case is 16. So pi 16 squares over 4 multiplied by 4 of them, and that will give us 804 millimeters squared. The center to center spacings between the bars is about, if we take 30 millimeter cover from the sides, it will be about 108 millimeters. You can round it off to, 105 millimeters or something. Now, the next step is to draw the stress and strain profile, primarily the strain profile of the beam, and write out all the important notation. So we should also draw the stress as well in respect to the curvature, but I will show you why the curvature is related mainly to the strain profile. We will discuss it here. So as load is applied on the beam, I'm going to experience compressive strain at the top of the beam and tensile strain at the bottom of the beam. Look, we have previously presented we've done a presentation on the Flexural formula, which thoroughly covers the stress and strain behavior of a beam, and I highly recommend you to watch it. You can click here on the link, I'll put it here so you can watch it, and it speaks a lot about the formula and how to derive the Flexural formula. Okay, now let's draw the strain profile for this section. So in most cases, in concrete analysis, we can start to assume that everything is linear. Plane sections will remain plane, which just means that this line will always be straight, and it can only rotate towards compression and tension. So as the beam bends, the line only rotates and it doesn't deform. The only time this line here can be deformed is when we have additional shear deformation in the beam, and this happens with very thick non-ductile members. So the very top fiber, which is in compression, we call that epsilon sub cc, which is concrete in compression, and at the bottom we have the concrete tensile strain and call that epsilon sub ct. This is at the bottom of the concrete, so it's all within the concrete. Then at the steel level, we have a tensile strain in the steel bars, and we call that epsilon sub st. Then we draw a line to the point where we have neutral strain, zero strain, and we call that dn, depth to the neutral axis. Okay. Now the depth to the neutral axis is always drawn from the extreme compression fiber, like shown here, to zero strain. Okay, it's from the compressive phase. Okay, so if the beam was hogging, let's say the beam was giving you a sad face, hogging the other side, then the depth would be taken from the bottom of the beam, because that will be compression, to the neutral strain. Then we finally note this angle here, and this is very important. We can call this theta, and the angle here represents curvature. Okay, curvature of the beam. Now, if we calculate the curvature from this triangle, this diagram here, it would simply be the strain of the concrete divided by over dn, which gives the units of 1 over length. Okay, the strain is unitless, and the units for dn is millimeters. So that's the units of curvature. So now we got this out of the way. As the loading P star increases, then the moment in the beam starts to increase, and then the compressive strain at the top begins to increase. So we will get contraction and the extension at the bottom, and so the strain, the tensile strain at the bottom will start to increase, and the overall curvature of the beam will also increase. And that's why it's important to document the moment and curvature in a diagram to see the behavior of the beam. And also, as loading increases, what do you think happens to the neutral axis in reinforced concrete beam, in concrete beams especially? It would rise towards the compressive phase of the concrete. Now, the rate and distance that neutral axis would rise would depend on the ductility of the beam. And ductility is obviously a function which is primarily dependent on the reinforcement ratio, and that is area of steel divided by B times DST, as well as the modular ratio, which is the modulus of elasticity of the steel divided by the modulus of elasticity of concrete. I guess we will go through ductility in a separate video. Now we will just focus on the moment curvature relationship. Okay, so here we have two axes. On the vertical axis, we have the moment value, and on the horizontal axis, we have the curvature. Now let's look at the beam's response to the loading at every stage. Okay, before any load is applied, obviously, we have no moment, and therefore curvature is zero. There's no curvature at all, unless it's pre-stressed, but that's a different story. So here we start at zero moment and zero curvature. Now we move up to stage one. As I start to apply my load, the moment will increase, and the curvature will also increase, but everything is still in a linear elastic behavior. And the line is linear. Again, when I refer to linear elastic, it just means that if you apply a load, it will slightly deform, and if you remove the load, it will come back to its original position again. All right, now stage two. As the load is increased, then the concrete first cracks in the tensile region at the bottom here, because concrete is weak in tension and there is no reinforcement right at the bottom. There's no reinforcements, obviously, so concrete will automatically crack. And so the crack will start right at the bottom there, at that face, and the crack will propagate to the reinforcement bars. Now, while concrete first cracks, then there will be some sort of discontinuity between the materials. So we will have this little step, right? This little step here. Now that moment associated with the first crack on the y-axis is called the cracking moment, which could be noted as m dash sub ct. Now, I have a question. So do you think that this external load P star was the only force, or the only two forces, which would cause that first crack? And the answer to that is no, because generally when we pour concrete, we have early shrinkage drying cracks, okay? And these cracks are formed initially before any loads. They create these tensile stresses at the bottom, and you get microscopic cracks within the tensile region of the beam. Okay, so we do have cracks, very minor cracks that happens due to the early shrinkage drying cracks. I guess in the next part of the series, we will talk about how to calculate the cracking moment, considering the shrinkage drying cracks as well. So yeah, let's continue with stage 3. So as we continue increasing the load, the beam is cracked, but it's still linear. Everything is still linear, and the moment curvature is still linear. And then we increase up until the steel yields, okay, at that point there. And the moment corresponding to that event, which causes the steel to yield, is called the yielding moment. And that could be written as m sub y. So at this point, my curvature has increased so much that my steel has reached the limiting strain value, okay? So steel bars, for example, with the yielding strength of 500 MPa means that steel will yield at 500 divided by 200,000, which will give you 0.0025. Okay, that's the yielding strain, which means that it is 0.25%. Okay, stage 3 is generally called the concrete in-service behavior, where we kind of expect some cracks and some sort of deflection, but the beam has not yet reached failure. Okay, stage 4. Now this is the fun part. As we continue to increase the moment beyond the yielding moment, we will start seeing a non-linear behavior. It's no longer a line that's linear. Okay, it's a non-linear behavior where deformation transitions into the plastic behavior. Okay, it will not return back to its original shape again. So so the moment curvature line starts to move sort of horizontally, and then increases slightly, then decreases a bit, and then fails. This failure point at the end is called the rupture point. The point that we are interested in when designing beams is this moment corresponding to this peak level here, this little curve here. This is called the ultimate moment capacity, or the nominal moment, and it is written generally as m sub u. At the ultimate moment, it generally means that concrete crushes at the top in compression. The maximum concrete strength, F-C, would have reached that capacity. At the yielding capacity, we must make sure that the compression has not reached, but at moment, yeah, we were expecting that F-C would have reached. This implies that the neutral axis would have reached so high in that compression zone, leaving no concrete left to hold any more compression forces. Okay, so the neutral axis will go up, right up to the top, and there's no more concrete left to hold any forces. So yeah, these are the four main stages in the moment curvature relationship with respect to the the single reinforced concrete beam. In the next parts, we will discuss the mathematical equations that define each of these moment values. Okay, the cracking moment, the yielding moment, the ultimate moment. And of course, we can work all of this out from a given stress or strain profile. So yeah, I think this wraps our discussion about the moment curvature relationship. So if you have enjoyed this video, please share, like, and subscribe so that others may also learn. Until next time, we hope that you have a great afternoon.